Today, I would like to talk about fabrication and characterization of nanomaterial-based sensor devices by metal organic derived solution treating method. This slide is showing the photo figures of the sensor device and SEM and TEM image of molybdenum oxide nanorod of the devices. You can see that the nanorods are almost single crystal. Today, I will talk this kind of oxide nanostructure synthesis by MOD method and making gas sensor device to evaluate gas sensing property of them. Okay, let's move to the introduction in this talk. Near future, we will get super smart society, which a lot of big data are getting from our physical space by IoT technology and all sensing systems. The big data are optimized and add additional value through the AI and ICT technologies and feedback actionable information to us. This concept is calling cyber physical system, CPS. The CPS will solve all social issues and develop new economical service and industries through the improving the productivity. The sensing devices are very important of the IoT technologies in CPS, especially gas sensing from our breath gas is effective method to get human condition for the healthcare. The breath gas includes many information for human health condition relationship with gas species. This table shows the relationship with physical condition of human with gas species and amount. Our breath gas from human includes more than 100 kind of gas species. We have to detect many kinds of and small amount of gas at the same time and at the same device and module. Of course, the sensor devices have to develop more good sensitivity property and cost-effective fabrication process and low energy consumption during the running. These figures and schematic figures show the traditional semiconductor gas sensing sensor module and devices. The detector consists with the 4 electrodes, and 2 is heater and another 2 is sensor devices, electrodes. The sensor device fabricates with this kind of counter electrodes on same rigid substrate, and then this kind of sensor, the nano materials deposited on the substrate. There are a lot of printing technology for next electric device production. We call the technology is printing electronics or printed electronics. That is we call PE technology. The PE technology mean use solution process and high performance printing technique overcome the concept of non-high vacuum process, non-photolithography, low energy, low material resources, and cost-effective methods. This slide shows that the y-axis is ink particle size, and the x-axis the mean curing time to use several sintering methods. Both axes decrease or reduce with this direction, and then the final goal is a roll-to-roll process printing. When the ink particle size decreases from bulk to molecule, the curing time can be reduced. Recently, we are focusing metal organic decomposition method to make nanostructure material and printing method of the cost-effective device fabrication. The figures show my strategy of the development of nanomaterial design by PE technology. When do you need bulk property of the, for example, large electric conductivity and thermal conductivity and so on? For the final product, for the final product electric devices, the starting material will be include nano or particle. So we may choose the nano ink for starting material for the electric devices. However, on the other hand, when do you need the property of nanomaterial such as big surface area, high speed reaction, and so on? You have to choose more small particle size in ink. The meaning the ion or atomic size level. So I think we have to make ink design down to ion or atomic level, particle size level, for using the nano or particle in the devices. In this reason of this study, we focus on metal organic decomposition method. We call MOD method. The MOD method means that is one of the film forming method of the metal or ceramics, which use precursor this kind of ink, including metal ion and organic compounds. The ink sintered with heat or the other alternative methods such as photo UV laser or so on sintering. After printed method and coating. In this study, we tried to nano structure shape growth on the substrate directly by using this MOD method. And in this study, fine is heat sintering for the sensing device, gas sensing devices to use large specific surface area for high-speed chemical reaction of using nano material. In this objective, in this study, fabrication of nanostructure oxide for gas sensor device by a simple solution MOD method and evaluate sensing property of the devices. Let's move to the experimental procedure. Easy to understand, I prepared a movie of the experimental steps in these slides. The starting material are mixed with magnetic stellar. After 30 minutes, this kind of precursor drop on the substrate and spin coat 10 seconds. After spin coating, the sample is put on the electric furnace already heated up to. And after sintering, we pick up from electric furnace. You can see that after sintering sample changed the colors from transparent to dark brown color. Okay, let's move to the result and discussion. We successful directly sintered gross nanorods on the silica glass substrate by the MOD method. The almost single crystal MO3 nanorod array grows randomly random network on the substrate. We published the results, these results with discussion of the growth mechanism on the paper of crystal growth and design. In addition, the XRD pattern data were accepted ICSD XRD database in 2016. We challenge to control the length of keep diameter of the nanorods by several methods. The length of the nanorods increased with increasing sintering time without increasing diameter after about 10 nanometer. You can see about 70 nanometer to 600 nanometer are each 3 to 15 minutes sintering. We can get the mechanism of the growth relationship with decomposition timing of the starting material of especially citric acid and amine. The relative citric acid molar ratio with molybdenate in the precursor may play a critical role in the crystal growth process of the nanorod. Then we try to make decomposition timing of citric acid and amine by using another method. You can see the figure. We change several solvent boiling point from 350 Kelvin to 400 about 50 Kelvin. So as a result, the length of the nanorod increase according with increasing the boiling point of the solvent. So we can change the mean length of the nanorod by controlling sintering time and boiling point of the solvent. The which suggests the critical citric acid and amine in the precursor may play a critical role with nanorod growth. The and in addition, recently we get mechanism of not only the nanorod growth length, but also thickness of the seed layer. The seed layer means you can see the figure of the under of the nanorod thickness. The seed the relative citric acid molar ratio with MO in the precursor also played a critical role in the nanorod growth and thickness of the seed layer. So we can be controlling the thickness of the seed layer without changing the length of nanorod and thickness of the also nanorod. So you can see the difference of upper side figures and the downside figure. You can see the transparent thickness of about 40 nanometer of seed layer thickness. However, doesn't change the length of nanorod and thickness. We fabricate the gas sensor device by the top coat forming top electrode at this kind of two counter electrode of the both edges at the both edges. The device put on the tubular electric furnace heated at 350 degrees Celsius. The VOC gas such as acetone, IPA, methanol, and ethanol are pumped into the furnace concentrated about 25 to 500 ppm. The resistance of the device are sensing with the on and off the gas blowing in the furnace. The time of response is defined that the resistance reaches 90% of the stable value. On the other hand, the recovery time is defined the resistance come back to 90% its initial values. And sensitivity is different resistance to the initial value, and the value are usually used a percentage expression. Okay, I will move to the result and discussion of the gas sensor property of the MoOx nanorods. The figure shows the normalized resistance response of the nanorod array gas sensor to 500 ppb ethanol. The resistance of the nanorod arrays immediately decreased with exposed ethanol vapors and increased in the ambient air. And to demonstrate response to the various gases, methanol, ethanol, isopropan no ethanol and acetone were selected as a target substitute to the evaluate the selective of the sensor at 550 degrees Celsius. The sensor shows the change in the resistance on the exposed to all the target vapors and changing at different magnitudes. The large response was to the ethanol vapor, with smaller response to the methanol, IPA, and acetone vapors. This figure shows the relationship of the mean sensing of the sensor to different concentrations of these VOC vapors. The sensitivity of the sensors increase linearity with concentration of all of the VOC vapors. Okay, let's move to the another material. I would like to show you titanium oxide nanostructure by same simple MOD method. Okay, let's move to the experimental step. This is the one of the example of the titanium oxide at the make from almost same from metal organ decomposition method. And we got the other structure of the same titanium oxide. This shape is sphere-like. We try to make the sensor device this kind of sphere-like material, and also can be detect at the about 350 degrees Celsius, and okay, time is over. I move to the summarize in this study. In this study, the random 3D network of the ultrafine single crystal MoOx nanorod arrays in large scale was bright gas sensor, which was grown by a simple and effective simple step MOD method. The sensitivity response time and recovery time of the sensors closely depended on the specific morphologies of nanorod arrays, which length, number, and coverage area of the nanorod. The titanium nanostructure also can be synthesized by simple step MOD method on large scale glass substrate and fabricate as gas sensor devices, which also can detect 1-propanol, methanol, and ethanol VOC vapor gas at low working temperature, about 350 degrees Celsius. The nanostructure oxides would open the universal application in gas sensor for variable vapor detection. And we can make the large scale, low cost, and primitive synthesis process of the sensing devices. Thank you for kind attention.